want to welcome you to my YouTube channel. In our previous class, we discussed about chemical kinetics, the basics of chemical kinetics. But in today's class, we will be talking about the zero order reaction and its half-life. And I said a zero order reaction is a reaction whose rate is independent on the concentration of the reactant. So assuming we have a reaction with reactant X giving us a product, the reaction rate of this reaction will be equal to negative change in the conc of X over dt. Just like I explained. Please, if you haven't watched the video, kindly do so. So the reaction rate of this reaction is equal to negative change in the conc of X over dt. And similarly, from our rate law or our rate equation, we're able to describe that the rate of a reaction is directly proportional to the conc of the reactant raised to power n, where n is the order of reaction. So in this case, we are talking about the zero order reaction, meaning that n here will be equal to 0. Of course, we change the proportionality to equal, and then a constant is being introduced, x. Since it's a zero order reaction, n is equals to 0. N is equals to 0 for a first order, for a zero order reaction. And of course, whatever has the power of 0 equals 1. This will give you 1. Therefore, R is equals to K. Let's call this equation 1 and this equation 2. So mathematically, if R is equals to this in equation 1 and R is also equals to K, it therefore means that equation 1 equals equation 2 equals to K. So it's R equals R. Okay, so I can move the negative sign over there. I have that the X. Similarly, I can decide to move this here, I will equal to negative K dt. So when I have a differential equation, d, the next thing to do is to integrate. I'll do that by introducing my integral sign. I'm integrating both sides. So I'll have integral dx is equal to, we don't introduce negative, so we don't introduce signs, negative or constant k. So we integrate delta t. Whenever you are asked to integrate the change of a variable, your answer becomes the variable is equal to minus k. Similarly, integral of the t becomes t. And whenever you are done with integrating, you have to introduce a constant c. Now we are faced with a question here, c. How do we know the constant c? To know the value of c, we have to say at initial time, then when t is equal to 0, it simply means that the final concentration is equal to the initial concentration. So we have to introduce these values in here. Then we'll have that x is equal to, when t is equal to 0, therefore whenever you see x, you put x naught, and then we have negative k t0 plus c. Anything multiplied 0 is gone, so I'm left with x naught c is equals to c. So it therefore means that the value of c at when time is 0 is equals to initial concentration of x, which is the reactant. Therefore, we'll bring this value back to replace c. Therefore, our final answer becomes final conc of x is equals to negative kt plus initial conc of x naught. So this is an equation for a zero direct reaction, meaning that for a linear graph you have y is equals to mx plus c. Meaning that if you draw a graph, you can determine these variables. If these are final conc of our reactant and we plot it against time, we have a negative slope. Of course, as you can see, our rate constant is negative, meaning that our graph will go this way. So the gradient, the slope of this is negative k, and of course our intercept is this x naught. But how do we determine the half-life of a zero Darcy reaction? We do so by describing. In our last video, we defined what half-life is. We say the half-life is the time taken for the reactant to, or a given substance, to reduce to half of its original size. So half-life is symbolized T half. So at half-life, it therefore means that the final value of x will be equal to the initial value of x divided by 2, because that is what half-life is. Half-life is simply the time taken for the initial value or quantity of that substance to reduce to half of its size. So meaning that in our equation here, wherever you find this, you substitute with this. Therefore we have, instead of writing this from here, we have x is equals to minus kt plus. So I'm going to replace this with this. Then therefore I'll have x naught over 2 is equals to minus kt half. In this now we're going to have half-life now, so I'll change the t to half-life plus x naught. Remember, we're trying to look for t half, the half-life of a zero Darcy reaction. So in order for us to make this a sort of formula, I can easily move this towards this side or whichever. I'll therefore have that x naught over 2, of course, from positive to negative, x naught is equals to negative kt half. Taking the LCM, you have 2 x naught minus 2 x naught is equals to negative kt half. Of course, 1 x naught minus 2 x naught gives you negative x naught over 2 is equals to kt half. When you have negative signs on both sides, they'll cancel out. So you are left with x naught over 2 is equals to kt half. So I can easily make my half-life T half subject of formula. I'll therefore have that. I'll have that T half will be equal to, you bring this down, you have that x naught over 2k. So that's the answer. So we have been able to get the half-life of x naught over 2k where K is our rate constant. From that equation, you can see that the half-life of a zero-order reaction is proportional to the initial concentration of the reactant. As you can see, it's proportional to this. So thank you very much. If you like this video, don't forget to like and also click on the red subscription button to get more videos. Thank you. Hello guys, if you find this video helpful, don't forget to give it a thumbs up and click on the red notification button to get more of my videos. Thank you.